Welcome you all to this session today. This is the week two's advanced session. And okay, we are waiting for a few minutes for people to join. Join fast. I'll just give a small intro of you in the beginning and then you can go with the session.
Yeah, right. Should I start or should I wait for the audience to join? Maybe I can give a pause of 1 minute and then
Yes,
you tell.
yes. Let's wait for 1 or 2 minutes, then we can start.
Okay. Okay.
I have posted message also. And how many people? Okay. In between the session, if you face any issue, just let me know. And
Okay. Okay.
thank you for coming today. Like from your busy schedule, I know it was hard taking time out.
Okay. So shall we start? We are already 2 minutes past and joined a bit late.
Yeah.
Okay.
Yes.
So
Yes. Okay. Let me give a short intro. Like I have prepared some.
joined a bit late.
Sorry.
Okay.
So hello everyone. Let me introduce you all to our amazing speaker of today's session. It's Aman Mundra. He is senior AIML engineer at PayPal, and he has, if I'm not wrong, 10 plus years of experience in the industry now. And he's a proficient data engineer and intensive experience in like many technologies and open source tools as well. So very excited for today's session. So over to you, sir.
Yeah. Hello. Good evening. So thanks for the introduction, Aditi. So maybe I'll add a few more points here. So my name is Aman, and overall I have 12 years of experience as a data scientist. My current role is all about building AI solutions and so I'll not waste much time in the introduction part, but then again, I wanted to talk a bit about my startup also. So currently, I'm doing a startup also. It's a full stack AI firm where we are trying to build AI solutions around LLMs, Gen AI, and all those things. The name of my startup is Welzin.ai, so you can always check out there. And yeah, so the topic for the day is model optimization and ensemble learning. Now, maybe I'll quickly tell about what is model optimization and what is ensemble learning. But the whole session is more towards advanced decision trees, right? So I hope that you all have attended the previous sessions about introduction to ML, how it is how it is done, what is supervised ML, what is unsupervised ML. But still, I'll take one slide on refreshing all those concepts for you, and then we will deep dive into decision trees and all those ensemble learning and model optimization methods. Okay, so it's like model optimization and ensemble learning combine systematic tuning and multiple models to maximize predictive accuracy and robustness. So by we'll discuss a little about many techniques that we can use to optimize a model and how to implement ensemble learning to get better at decisioning, right? So the agenda for the day is, wait, let me go to the next slide. Okay, so that's a quick introduction about myself, about the topic, and then the next slide. Yeah, the next slide talks about the agenda, what all we are going to discuss here. We are quickly going to, so this is on the right hand side. If you see, I got this the list of topic from the team that I'm gonna speak about random forest, XGBoost, light GBM, and then hyperparameter tuning, the types of tuning that we can do, that is grid search and random search. Why, when do we do grid search, when do we do random search, and what more techniques do we use for cross validation, and how do we do decisioning in case of in scenarios where we have class imbalance. So I got this list, and according to that list, I prepared this deck and this agenda. So the agenda is pretty much clear. We'll quickly refresh and review about machine learning concepts. Then we'll deep dive into decision trees. This is kind of refresher where I'll quickly tell you about what is decision trees, when do we use it, and then we'll deep dive into ensemble trees, that is random forest, XGBoost, light GBM, what are these algorithms, when to use which algorithm, and the concepts around it. Then we will talk quickly about boosting and bagging. So boosting and bagging are the two techniques on which all these ensemble algorithms are built. So random forest is kind of a boosting technique. Random forest is a bagging technique. XG boosting, as the name suggests, is a boosting technique. Similarly, light GPM. So we'll quickly talk about boosting and bagging also, when to use what, which algorithm use which technique, and what is the differences between all these techniques, right? Then the next slide will cover about the hyperparameter tuning, or we call it model optimization also, that once the model is, once you set up the model training part, you tweak some hyperparameters which help you to get maximum optimization and maximum efficiency. We'll talk about the ways of hyperparameter tuning. Then I'll quickly talk about the class imbalance, that how do we handle class imbalance and what exactly class imbalance is, and all those details. And if time permits, we'll quickly talk about. I'll give you some time to kind of get your questions and answers and all those things. So we'll try to wrap it up in 1 hour. Already we are a bit late. So I also don't want to keep you waiting for on a Friday evening. It's a Friday evening, right? Weekend is ahead. People are already in the weekend mode. At least I am in the weekend mode. But still, we'll try to keep it short and crisp. And I'll try my best to kind of finish it within 45 minutes to 50 minutes, and then leave last 5 or 10 minutes for any questions and answers also, right? So the big picture of the whole topic is that how we move from decision trees to the advanced decisioning using ensemble techniques and ensemble algorithms, and how do we get optimized and efficient models, right? And all the things that we're going to discuss today is built on top of decision trees. So decision tree is the main foundation, and then on top of that we have built next things. So the next slide will definitely talk about the decision trees. Okay. Yeah. So what are decision trees? Now, before we deep dive into decision tree, like I said, I'll quickly cover what is ML. So under machine learning, you all know we have multiple types. One is the supervised machine learning, then unsupervised machine learning, then reinforcement learning, or we call it RL, and then deep learning. And these days we have neural networks and Gen AI also into picture, right? Where we are training large language models, correct? So if I go with the industry standards, 70% of time we are doing supervised machine learning. Even in my day-to-day work also, practical world as well, we are mostly doing supervised machine learning. And under supervised machine learning, we are majorly doing classification and regression only. There are cases and scenarios where we do use unsupervised machine learning or reinforcement machine learning also, but the use cases are very less. Or I can say that the topics are really advanced and we have very minimal use cases, right? So I'll quickly talk about supervised machine learning, and maybe I'll ignore reinforcement learning and unsupervised machine learning here for this class, because they are not relevant to the topic, right? So, what is supervised machine learning? So, in case of supervised machine learning, we have the labels, we have the label data. By label data, what I mean is, let's say I have pictures of cats, and I know all these pictures are cats. So this is the label data for me. Now tomorrow, if I give another picture of cat to my model, it will be able to identify it as a cat, because by learning all the patterns from the label data, we can understand, we can train a model which will identify a new image also as a cat. So that's the beauty about the supervised machine learning, where the data is already labeled for us, right? So when the data is already labeled, what we do is on the top of this labeled data, we train our model using different algorithms, and we get a new trained model. And to this model, we pass our new input data and get the outcome as a label data, right? And that's what you will see in the sheet also. It's mentioned that in case of supervised machine learning, the input variable is x and the output variable is y. And how is y generated? By learning on top of input variable x. That means the outcome of a model is the function of the input. The simple statement in maths also we see that, right, when we read about functions. So in case of supervised machine learning, the outcome y is simply a function of the input x. Now how this function is built or trained is depending upon the algorithm and the use case. Okay. So under supervised learning, there are mainly two kind of problem statements that we try to fix, or there are two types of machine learning models that we build. That is classification models and regression models, right? Under classification and regression, again we have multiple algorithms available. Now decision trees come under classification. Now what is classification and what is regression? In case of classification, we simply classify a variable as true or false. For example, whether someone is a cat or a dog, red or blue, where we have only classification that someone is COVID positive or COVID negative. This is classification where we have only two or three different classes for any particular value x. Right. Similarly, it could be male, female, or these days it could be LGBTQ. Right. So that is the classification in case of classification problem, where the output variable is a category, we call it a category. A category could be male or female, it could be red or blue, right? These are all categories. A person could be COVID positive or COVID negative or neutral. These are all the categories, right? And classification can be of multiple types. It could be binary classification, it could be multiple classification, or ternary classification. Now, male or female, COVID positive, COVID negative, it's a binary classification. Now, let's say colors. Colors can be red, blue, black, green. It could be many categories available in the colors, right? So that becomes multi-class problem statement, right? Where we have multiple classes, right? Similarly, the next scenario for supervised machine learning is regression. Now, in case of regression, we don't have anything called categories. Instead, we have the output variable, or we call it a continuous variable, right? So there's a simple way to understand. In case of classification, we have a category. A category can be color category, gender category, or any such thing, true, false, right? In case of regression, we have a continuous variable. The continuous variable can be speed, currency, dollars, or weight. It could be anything, like weight could be anything from 1 to 100, right? Dollars value can be anything from 1 to 1 million, right? Similarly, speed of a car can be anything from 1 to 100. So wherever we have a continuous variable, that problem becomes a regression problem. So there are multiple algorithms which we use to solve regression problems also, right? But for today, the problem statement is decision tree. Decision trees come under the problem of classification. So we have machine learning. Under machine learning, we have a category called supervised machine learning. Under supervised machine learning, we have two categories: classification scenarios and regression scenarios. Under classification, there comes decision trees. So decision tree is one form of solution which can help us to classify. There are many more algorithms also under classification, for example, SVM or KNN. So these are all algorithms under classification which help us to do prediction and to classify the data. So decision tree is the simplest and the best way these days in the practical world to do classification, or to perform or to solve the problem of classification, right? So simply, decision trees are simply a tree-like structure which has nodes and edges and leaves. In case of machine learning, we have leaves also, and all these nodes and edges are kind of traversed on the basis of conditional statements. Now, these conditional statements can be anything which will lead us to the decision, right? For example, if I say, okay, classify between a bird and an animal, how will you make a decision tree? If the condition would be like this. If that animal has feather, then it's a bird. If the animal has fur or a tail, it could be a bird or an animal. But if it has four legs, then definitely it is an animal. So that's how we make the decisioning, we make the conditions, and we identify or classify the animals. Simple, right? So that's how decision tree works, right? Where we classify the data based on the conditions we put. Correct? I don't know if you can ask me questions directly, but feel free to add it in the chat box. Maybe I'll try to reply them on the fly or maybe after this meeting. So yeah. Okay. So decisioning tree is one of the algorithms that is present under classification, and classification comes under the category of supervised machine learning, right? So that's the foundation of ensemble techniques, right? The reason why so there are so decision trees are just the theory. In practical world, we are not using simple decision trees like you see in this diagram, right, on the top left. In the practical world, we use advanced versions of decision trees, and those advanced version of decision trees come under the ensemble method of training a model, right? Now let's go to the next slide, which will talk about ensemble methods. That is actually the core of our meeting today, right? Because we have to talk about ensemble methods and ensemble trees. Now, what are ensemble trees? Ensemble trees simply are a mixture of multiple decision trees which help us reach the decision. Now, there are multiple techniques and multiple approaches to collect or mix all these trees together and get the best output. Right? These techniques are bagging and boosting. We'll talk about bagging and boosting in detail maybe in the next slide. But for now, I want to talk about the examples. Now, there are three examples that you see here, which are ensemble tree algorithms. One is random forest, or we call it RF in short form. Second is XGBoost. Third is LightGBM. Right? So these are the three algorithms mainly which are used in the industry to perform classification using decision trees. I have personally used XGBoost and LightGBM models a lot. So I would definitely suggest all you guys to read in detail about what is XGBoost, how it works, how do you implement it, and simply how do you use LightGBM models, right? In practical world, you will never work on plain or vanilla decision trees or SVM or KNN models, but you must know about all these algorithms, because once you will know about decision trees, KNN and SVM algorithms, then only you would be able to understand the advanced algorithms. For example, for in today's case, it's decision tree. Similarly, under SVM or KNN also we have multiple advanced algorithms which we use in practical world. So in case of decision trees, these are the three algorithms that we use in practical world: random forest, XGBoost, and LightGBM. Now we'll cover these algorithms one by one. But before that, I wanted to talk a little about ensemble trees, what exactly it is. So, like I said, like I've mentioned in the sheet in the slide, so ensemble trees are simply a combination of multiple decision trees which act and work together to improve the accuracy of the prediction or the outcome of your model, right? Why we need ensemble technique? It's simple. A single tree with multiple conditions will give you lesser accurate results. That means that a simple tree might overfit. But in case of ensemble trees, it will give you better results by leveraging the wisdom of multiple trees in its ensemble, right? That's why we call it ensemble trees. Here we simply use hundreds and thousands of trees together with different properties, with different hyperparameters tuned according to the requirements, and then we get the final output, right? So the first one, random forest. Just a minute. Yeah. So what happens in random forest? It's very simple. It's the simplest decision tree which we use in the practical world, right? So in case of random forest, we will simply randomly train hundreds of trees based on random data samples and features. What we'll do is, let's say I have in my while training a model, in my input data, let's say I have 100 features. Out of 100 features, what I'll do is I'll train 100 different decision trees based on 100 different random data and different features. In one case, I'll give top 10 rows and only 10 features. In second case, I'll give last 10 rows and any 20 features. In third scenario, maybe I'll give 50 middle rows and any 50 top features. So like that, I'll randomly select 100 or 200 different data samples and 100 or 200 different features. The number of different data samples that you want to take or the number of features that you want to take could vary depending upon the time you have, depending upon the data, and depending upon the infrastructure you have, because ultimately you have to train all these 100 random forest trees, right, and then get the outcome. So this number can vary, but all I'm saying is, in case of random forest, as the name suggests, just take random data samples and random features and train them on a simple decision tree. Once it is trained, collect all the patterns that you attained, and give them vote. The tree with the highest accuracy or highest vote will be your model, or will act as the champion model, right? That is what happens in random forest, and it's called bagging, because we are making small bags of data with sample data, sample features. We have made 100 bags, and out of these 100 bags we will pass our input data and get the output. Now whichever output is giving us the most accurate results, we'll pick up that bag with that sample and that list of features. This way we'll get our champion model, and this will act as your champion model, and you will deploy it in production. That is what happens in random forest or in bagging technique, right? Now, why a random forest is better than a plain or vanilla decision tree algorithm? So the reasons are multiple, since it will definitely improve the accuracy, and by that it will reduce the overfitting. Why it will reduce the overfitting? Because now you are taking averages of hundreds and two hundreds of trees, which are trained on top of hundreds and two hundreds of different data samples and features, right? Because all these trees are of different nature, they will have different data set or input, and they will have their different output. That's why we call it random forest, and that's how it reduces the overfitting and improves the accuracy of a model. And it's the simplest one and the fastest one, right? So that's how random forest work. Now the next one is XGBoost. Now XGBoost is also a really widely used algorithm in practical world. Even I kind of use it for every classification problem. So XGBoost is my go-to algorithm for tackling any uh, classification problem, right? Now what happens in XGBoost? It's a little different from random forest, right? So what happens is, we call it sequential decision tree learning. Why we call it sequential tree learning? Because here we create a one random tree. We create one tree and get the output and see the mistakes out of that tree. We then create next tree by fixing those mistakes. Then we create next tree by fixing the second tree's mistakes. Then we create the fourth tree by fixing the mistakes of the third tree. So this iteratively we'll do this 1,000 times or 500 times. Again, depending upon the data you have, depending upon the CPU and computational resources that you have. So we do this iteration like 100 or 200 times, and in the end we get the final tree, which is built on top of previously fixed trees, right? And this way we will get a really good, powerful, and most accurate tree, which has less bias and more variance. Correct? Simple. Now you understand how it is different from random forest. Here we are not selecting the trees randomly. First tree is selected or made randomly, and the next trees are built on top of the previous trees fixation issues, right? That's how XGBoost works. Now the last one is the light GBM. So here the light GBM model is little more faster and more memory efficient, and it's little better than XGBoost when we have less time and less computational resources, right? Now what it does is, it will simply create, it will do the tree, it will do the decisioning based on the leaves. So in case of light GBM, what will happen is, multiple layers of trees are accessed, and the last leaves are the ones which will act as the final trees. They will be collected together, and then a final tree is created. Right now, light GBM generally gives you better results when you have variety of data, when you have large number of classes in your data, For larger data sets, we generally use light GBM because it has higher speed and it uses less memory, right? So in cases of machine learning, you will not deal with 1,000 records or even a few thousand or a few lakh records. No, in big data and in practical world, you will deal with more than 10 million or 20 million records, even a billion records. At PayPal, I used to work on more than a billion records. So out of these billion records, you will take a sample of a few million, and these million records also will reach a few TBs. Now, when you have to process and churn these TBs of data, running an XGBoost model is a time-consuming process. It's computationally heavy and time-consuming. That is where light GBM kind of works better, because light GBM performs much more faster and efficient than XGBoost, and it gives much better results. So whenever you have big data, whenever you have large data sets, we prefer to use light GBM. Also, the reason why to use light GBM is when you have large data set, when you have big data, it's really hard to understand the data. So that is when you rely on light GBM. That you will say the data is huge. I don't want to waste my time on properly understanding the data. Let light GBM do its wonders, and let light GBM give me the final outcome. Right. So that is what happens in light GBM. And someone in the chat box had asked Aditi Chaudhary that is XGBoost like the epochs in neural networks. I would say somewhat similar, but not exactly epochs, because in case of neural networks, there could be like millions of epochs, right? Because in neural networks, again, we have billions of records, and there will be multiple layers of epochs through which the data will be passed, and in the end, you will get a highly trained model. You can say that from analogy point of view, you can say that, but the concept's a bit different. In case of XGBoost, the whole decision tree is kind of built from scratch. That does not happen in case of neural while training a neural network, right? So conceptually, it's different, because in XGBoost we create a new tree from the previous tree by learning the mistakes from the previous tree. That is why it is called boosting. That is, you are boosting the performance of next tree based upon the previous tree's outcome. And in while doing this process 1,000 times, you would be able to boost it till the end, right? That's what happens in the XG boosting. So yeah, so these are mainly three decision tree algorithms which we use in the practical world based on the kind of scenario that we have: random forest, XGBoost, and light CBM. I mean, if you, I mean, from experience and practical point of view, you must know all these trees, and you must know the scenarios when to use what. Okay, so okay, I don't know if you guys are able to ask more questions, but I'll quickly jump to the next slide. That is, yeah. So this slide is about boosting and bagging, like we discussed, that all these decision trees which we discussed are based on two techniques: boosting and bagging. Either the advanced tree will work on boosting, like XGBoost, or it will work on bagging, like random forest, or it could be a mix of both, like light CBM. Right now, before we talk about boosting and bagging, I want to talk about two concepts called bias and variance. So these are the two things which are really important while understanding the decision trees, and while dealing with the data, or while dealing with the classification problems. Okay, so before I talk about bias and variance, I'll tell you the goal. The goal is we want low bias and low variance, and there is always a trade-off between bias and variance which a data scientist had to take care of. You cannot go with high bias, low variance, or low bias, more variance. The bias to variance ratio has to be in a proper balance. We call it a bias variance trade-off. Now, what is bias? Bias means Bias means once you train a model, how far off your outliers are from the average, from the model predictions. So bias simply measures how far, on an average, a model's predictions are from the true values. For example, let's say there are four colors: red, blue, green, yellow. Now, if your model is predicting black, it's totally away from the actual classes. That means it's highly biased, right, from the average. For example, there could be another example that let's say there are mostly, uh, let's say there are three categories A, B, C, right, and most of the data is falling in the category B. Now there are some points which are falling in some other category which is too far from the average. So that means the model is bit biased. So we need to lower the bias. Then there are methods to lower the bias, right? So there are multiple things in bias. A highly biased model will make strong assumptions about the data, which will lead to underfitting. For example, to make it clear, if a model is highly biased, it will try to predict all the outcomes which are near the average. If the average number of, let's say, if the average number of uh, population in Indian cities is, let's say, 1 million, and if the model is biased, it will try to predict 1 million only for all the cities, right? So okay, Khushi has asked a question that does bias happen based on previous learning or is it random? No. So bias is in the data, bias is not happening in the model. No, bias is in the data. A data is biased. Because the data is biased, that will reflect in your model also when you train it, right? So it may happen in any case. It can happen in random forest also, or in your boosting algorithm also. But mainly bias will happen when you have undersampled data. So the way to tackle biasness is by properly sampling your data and then giving it for prediction or training. Okay, that is bias. Now the second term is variance. Now variance measures how much a model's prediction vary from different training data sets. That is how sensitive a model is for all the random fluctuations that you have in the data. Okay, so in case of bias, we saw that it always underfits. In case of variance, when a model has high variance, it will overfit the training data and it will overfit very closely to the data, including the noise also. That means it will not. By overfitting, what we mean is, if a model is highly variance, it will overfit. And by overfit, we mean that whenever unseen data is sent to your model, it will give you very poor results. That means that we mean by overfitting. And why overfitting will happen? When there is high variance in your model. Okay. For example, the simplest example could be when your simple decision tree is very deep, right? For example, when you have when you train a decision tree which is so deep that it perfectly fits the training data, that is, it has very low bias. In that case, whenever a new data is given to this really deep decision tree, it will try to predict from this decision tree only. It will try to overfit, and that will give you wrong predictions for any unseen data. So there has to be always a balance in the length or in the height of the decision tree, right? We cannot become so granular that your decision tree has like more than 200 levels. That way it will overfit and it will lead to variance or high variance in your model. We don't need that, right? There always has to be a balance between bias and variance, right? So that's the goal of training model, that we have to find the right balance between bias and variance. Both of them should be low, right? And the model complexity also depends upon that, right? So this trade-off is called bias and variance trade-off, right? Now this is about bias and variance, and now we can switch to the bagging and boosting, like what exactly happens in bagging and boosting, right? So bagging algorithms are simply bootstrapped aggregating or bootstrapped aggregation, where a bagging model builds multiple independent models or decision trees in parallel. That's why it is called bagging. So in case of bagging, multiple independent decision trees are made in parallel, and each decision tree is trained on the random data sets and the random features. The perfect example is random forest. So random forest is a bagging model where multiple decision trees are trained in parallel for different set of input data and different set of input features, right? that is simply called bagging, right? So the predictions that we get from these bagging models are very combined or very averaged, because all these let's say we will train let's say 500 bag models in parallel, and then we will average out the prediction and get the final model or the final result. So it will give you a really good averaged result of the model, and definitely improving the accuracy from the plain vanilla decision tree, right? So bagging generally helps us reduce the variance. By variance, what we mean when the data is varied. How do you reduce the variation or varied data? By averaging it, right? That's what bagging is, and that's why it prevents overfitting. We discussed, right? High variance leads to overfitting models. So if we reduce the variance by averaging it, by bagging it, we will simply prevent overfitting, right? And how we will do it? By leveraging the wisdom of thousands of crowd models or thousands of crowd decision trees which we have trained using random forest technique or using the bagging technique, right? That is what bagging is. Now the next technique is boosting. Like the name suggests, we have the XGBoost model, which is based on boosting technique. Just like we discussed, how the model works by building its next decision tree based upon the outcome of the previous one. So boosting is simply a sequential model training where the models are trained sequentially from the previous decision trees or from the previous models. And during the sequence, each model attempts to fix the errors made by the previous decision tree model by focusing more on the difficult cases, right? So what happens in boosting is we sequentially train multiple decision trees, and each consequent decision tree is built on top of the previous decision tree by fixing its errors and mistakes, right? And all these predictions for all these decision trees that we train sequentially are combined together, weighted together, and then in the end, on the basis of all these weighted combination, we get a boosted model or the final or champion model, which we call XG boosted final model or champion model, right? So in case of bagging, we were averaging all the decision trees. In case of boosting, we are combining the results of the previous decision trees by fixing them, and in the end, we get the final tree. Here, we are not averaging, we are combining the weighted outcome or weighted average of every tree. That's the difference between boosting and bagging. And the perfect examples are XGBoost model, ADA boost, light GBM. Now, to understand XGBoost and light GBM model, ADA boost also is one good model, which is a basic model which one should know how boosting works, how XGBoost works, right? Now, similar to bagging, boosting models also reduce bias and variance both, right? In case of bagging, bias was not reduced. In case of bagging, it was only tackling variance. If you have varied data, build hundreds of decision trees on this variable data and average it. By averaging, you will reduce the variance. By reducing the variance, you will reduce the overfitting of the model, and model will give you better results. In case of boosting, we reduce both bias and variance by training multiple models in sequence and fixing it iteratively, right? That's how boosting technique is little better than bagging, but it takes more time to train a model, right? So boosting methods generally take more computational power and more time to train a model because we have to do it sequentially, not parallelly. Bagging is happening parallelly, so we can use all the CPU cores together in parallel. But boosting is sequential method. First tree will be trained. It will take a few seconds. Next tree will be trained on the previous tree. It will take another few seconds. Then third tree, then fourth tree. So in this way, in sequential manner, it will train, and we'll get the final tree. So that's why boosting algorithms are a bit slow and are a bit computation heavy. But the perfect examples are XGBoost and LightGBM. We use it every day in every practical world, right? So that's how you differentiate between bagging and boosting. Bagging is parallel, boosting is sequential. Bagging reduces variance, boosting reduces both bias and variance. Bagging builds strong ensemble algorithms by averaging over many independent learners or decision trees. Boosting build strong ensemble decision trees by learning from previous trees and by correcting their mistakes, right? So that's how bagging and boosting work. Correct. If you have any questions about it, you may put it in the chat box. I'll try to answer it, or maybe I'll try to reply it in text later. But this is how bagging and boosting works, right? Now, going to the next slide. Yeah. So the next slide is about hyperparameter tuning, or there are two methods in hyperparameter tuning: grid search and random search. Now, what is hyperparameter tuning? Hyperparameter tuning is simply the process of systematically searching for the best settings or fine tuning the parameters of your ML model according to the dataset and features that you have. Simple. Now, what we do in hyperparameter is we tweak we tweak the parameters and we select such configuration choices before the training, like how much should be the tree depth, what should be the learning rate, what should be the number of estimators, how many leaves should be there, how many iterations should be made. So there are like 20, 30 list of parameters that we tune. We call them hyperparameters for a decision tree. We tune these parameters according to the data, according to our experience, and according to the scenario. We tweak these parameters and then we train the model and we get the accurate results. Okay, so this is not, this hyperparameters are not something which are learned from the data. No, you as a data scientist you will deploy your skill, you will put your mind, your experience, and your knowledge about the data to tweak and select the hyperparameters that you want to select and tweak. So hyperparameter tuning is not something which is written in books, or there is no formula for selecting or deciding the hyperparameter tuning. Hyperparameter tuning kind of comes with experience, when you solve multiple problems, when you spend day in and day out and hours of training the model for different use cases and scenarios. So with experience, you will understand what parameters to tweak for what kind of scenarios, like tree depth, learning rate, all those things. So this comes up with experience, right? Now, the most common methods for hyperparameter tuning are grid search and random search. So simply put, a grid search is to simply try all the possible combinations from a preset grid, right? There are like let's say there are 10 different parameters that you can adjust. So grid search says you test and try all these parameters, all the possible combinations that you have, and then you get the model. Simple. It's like a brute force way of telling the model to try all the different or possible combinations, right? Random search, like it says, it simply randomly select combinations of parameters, and whichever works faster and whichever gives you better results, use that, right? So that is what happens in grid search and random forest. Random forest is good when we have very less number of parameters and very less number of options. Sorry, grid search, my bad. Grid search generally works when you have lesser number of parameters. Let's say you have only 5 parameters to tweak and there are 2 or 3 different options. So by permutation and combination, you get roughly 15 different possible combinations and you can do a grid search. Random search is for larger data sets where you randomly select the best parameters that can go well according to your experience and then train a model, right? So in case of grid search, we exhaustively brute in a brute force manner, we try to cover all the combination or all the possible combinations. But in case of random search, we selectively pick one good combination based on the random search samples and the random features, and then start the training and or hyperparameter training, right? So in case of grid search, we get a really good output because we have tried all the possible combinations, so definitely we'll get the output, right? But in case of and it is time consuming. But in case of random search, we do get a good output, but it is time consuming because we are trying to save our time by finding the closest solution by tweaking selected set of parameters. we are trying to train the model which is the closest solution. So it is fast, but takes less communication, less computation, and it's efficient, right? So in case of grid result, we will get accurate results, and it's computationally heavy, but it will take some time to complete, but we will get good results. But in case of random forest, the results will not be the best ones, but they will be much more accurate, but they will be faster. When we have big data, when we have billions of records, we generally go with the with the random search. Why? Because we do not know the best parameters to tweak. So we let computer decide. We let the algorithm decide and give us the results, right? So that is what happens in hyperparameter tuning. Two ways: grid search, random search. Do grid search when you have less data, you have lesser number of combinations and lower classes. Do random search when you have big data, when you have more data, and you have hundreds of combinations possible. Then you pick and choose and select the best ones. Okay. So the next slide is about the class imbalance. I think this would be my last slide. This slide talks about how do you handle the imbalance in your class. So here, what is a class? In case of classification, like we discussed, we have multiple categories. Let's say I am trying to classify colors. It could be red, blue, green. These are my three classes, right? Now let's say in my data set, 90% of data is of blue color, and another 20% data, 10% data left is of color red and green. So this shows that my data set is imbalanced. The class is imbalanced because 90% of my data is inclined towards one class, that is blue color, right? So that is where the class imbalance works. Now, decision trees tend to underfit or tend to perform lower when there is high class imbalance, right? So, like the definition said, class imbalance occurs when you have data concentrated towards just one class, right? For example, if you say if in during the COVID wave two, everybody who was in Delhi was getting COVID positive, right? So that means the class was imbalanced because everybody was coming out to be COVID positive, and even if someone is not positive, still he or she will feel that he may have got COVID, right? So there was a high balance of uh, COVID test positives and false positives and false negatives, right? So that was a clear example of class imbalance, right? And this is really common in cases of anomaly detection because when you deal with IoT data, let's say you are dealing with sensor data or IoT data, right? In case of IoT data, we have sensors. A sensor will either perform or not perform. Either a sensor will give you random values or it will just not give you the correct values. So in case of anomaly detection, there is the class is imbalanced. Why? Because 98% of the times your sensor is giving you correct data. There will be one scenario where we where the data will be incorrect or there will be anomaly that you will have to figure out, right? That this is a perfect case of class imbalance. So in case of class imbalance, uh, it's very hard to create balanced decision trees which can take care of this class imbalance. So there are multiple methods that we can use to kind of tackle this imbalance in the class, right? So on the top left, I already discussed about the problem, that what is the problem with the class imbalance, because if the majority of the data is concentrated towards one value, the model will not perform well. It will tend to ignore the minority class, and that's what happens in the practical world also, right? The government tends to forget the class which is in minority, right? The schemes are made for the majority ones, right? And that same thing happens in the model. If the class is imbalanced, the model will shift its decision towards the majority class and tend to ignore the minority class, and this will lead to incorrect prediction or underfitting of a model. Just a minute. Yeah. Okay. So this is the problem. Now, how do we fix it? So there is one way that is to fix it, and that is resampling methods. So there are two ways under this problem, that is oversampling. So if we try to sample our data properly, if we do not go by random sampling, if we already do due diligence during our EDA or exploratory data analysis that okay, that hey, the class is imbalanced. Before we train the model, before we select the training data, we need to resample it properly. Now, how do we do this? If I already know that my class is 90% biased or shifted towards blue color, what I'll do, I'll take the samples properly. I'll take 5% samples from all the three classes available. I'll take random 5% samples from blue data, random 5% samples from red data and green data. Maybe from blue data, I'll take 15% samples because obviously there are more samples. But I will make sure, I will ensure that I pick a good ratio of records from the minority classes as well, so that my sample data is balanced, so that my sample data has mixed set of records. Once I have done this sampling, then I will push this data to my training model, and then my training model will be able to perform much better than a randomly selected sample class, right? So that's how, that is one way to tackle class imbalance, where you do resampling, where you resample the data once again, right? So that's how we do sampling and resampling, right? So so this is, I think, about the class imbalance. How do we deal with class imbalance, uh, and how do we resample the data properly by doing proper exploratory data analysis on our data. That is why it is said. So you must have heard about this statement, right? That given a task, don't just jump into the execution. Plan it properly, plan strategically, and then move towards execution. Spend 80% of your time in planning and then 20% of your time in execution. Same goes with machine learning. While training a model, while doing decision, spend 80% of your time on the data, on understanding the data, on doing exploratory data analysis, on understanding the classes available, categories available, uh, if there is any imbalance, all those things. Once you have understood the data properly, the classes are available properly, then you decide what model to use, what kind of sampling you should do, what kind of hyperparameter tuning you should do. You will be able to select perfect model, perfect parameters to tune, and perfect algorithm to train very easily if you spend your maximum time in understanding the data, in doing exploratory data analysis, running your running your input data through multiple statistical analysis, checking mode, mean, median, trying to figure out the data diversity that you have. If you do all this due diligence, you would be able to think better, pick a better model, pick a better algorithm, and get accurate results, or more, or I would say better results or better outcome and better prediction in lesser time, both in terms of cost and both in terms of time spent on training a model. Because training a model is an iterative process. You just don't get it right in the first outcome, right, or in the first cycle. You do it iteratively. You do it multiple times with multiple algorithms and multiple data sets and feature sets, and then in the end you come out with the final model. So Khushi in the chat box has asked that is it possible to, I don't know if you're able to read the questions, but I can see that. So she's asking, is it possible to check for imbalance before model training? If so, then how do you check the same? Like I said, yes, checking the imbalance is the first step. We have to do this before the model training. We have to check the data, we have to check the imbalance in our data before even we train the model. That's what the slide tells about, right? That handling the class imbalance. So what we do is we will analyze the input data properly. We'll check for the majority classes and minority classes. We'll check for outliers. Now I have not covered outliers here, right? Sometimes we tend to ignore outliers, but we cannot ignore that, right? So we do that. This exercise is done before we train the model, right? we check for imbalance by these methods, and then we accordingly decide how do you sample this data and how do you train this data, right? So now how do we check for imbalance? Like I said, we run the data through multiple statistical analysis. We check for the percentages, we check for the deviations, we check for the groupings, and then what more? We do aggregations on this data to check for class imbalance, and then we come up with the best sample data, and then we push the sample data to our model and then train that. Right? That's what happens in handling class imbalance. Right? Okay. I think I am done. So with this, we pretty much covered about decision trees and ensemble method. XGBoost, when to use YGBM, how these models help and work in the practical world. When you have big data, you use LightGBM. When you have imbalanced data, do your exploratory data analysis first, and then pick and choose the model and algorithms. How do you deal with class imbalance? Why it happens? What is bias? What is variance? What is bias variance trade-off, why we should keep it low, how do you keep it low. So all those things we discussed. So all these things will will should run in your mind before actually picking up a model and training it. Right? So as a data scientist with experience, you would be able to answer all these questions step by step first. And once you have answers to all this, then you would be able to perform better. Right? So I think that's an end from my end. Before I leave the stage for any questions and answers, there's one request. I think I have only 3 or 5 minutes left because I had to jump into another meeting because the US guys are on now. I have to jump in a meeting with them also. So if I'm not able to answer your questions right away, please post your questions. Maybe Aditi can send me the list of questions. I
Yes.
can answer it over the email or something. But another thing is, we at Belzin are looking for good people for internships and for job. I am looking for someone who are really good into AI ML space, prompt engineering, who has a passion to work in Gen AI space, LLM models, building RAG pipelines and agents. So if you have that, if you want to work with me, please reach out to me. I have mentioned the details, and I think I'll share this slide also with you guys. Maybe you can share it with the team, with
Yes,
everyone.
I will share.
So yeah, that's from my side. Thank you. Any questions? So yeah. So guys, I think I'll take 1 or 2 minutes of pause, and then I think I might leave because in just next 3 minutes my other meeting is coming. And also, I think we are
Yes, yes.
perfectly on time. We ended it up in 57 minutes. So considering 1 hour, I think it was a good session.
Thank you so much for coming. It was a Friday evening, and everyone who has joined the live session also.
Correct.
It was great to have you on. And
Great.
even my doubts like bagging, boosting, I also used to have like confusion in it. So I also cleared my doubts as well.
Correct. Correct. Sorry, I think now I saw the questions yeah, sent by you. I wasn't able to see the questions. So there are these two, three unanswered questions by Aditi about XGBoost complexity reduction, and then elaborate more on false positive and false negative. I'll do one thing. I'll send the answers to these in proper text. That would be helpful for everyone. Right? But maybe now we can end the session.
Yes, yes, sure.
I'll
Thank you so
definitely answer
much.
these questions. Yeah, I'll send it to you.
Yes, I will send it forward to everyone.
Correct. Yeah, just send me the questions, whichever unanswered questions are there. I totally kind of missed a few questions here. Some of the questions I was able to take up, but please feel free to send these questions to me. I'll definitely send you the answers tomorrow. Anyway, it's a weekend, so I can answer these questions. And for any other random questions, also you can always reach out to me via LinkedIn and all. I would be happy to help. The responses could be delayed considering the time constraint, but I'll try to answer. Cool. Okay, then. Thank you. Have a nice day. Happy weekend. Bye. Nice to talk to you.
Yes, okay.
Thank you.
Let's end the stream. Thank you, everyone.
Bye.